So as Carolina just said, my name's Steve Gillett. I'm a sales director at Hexagon PPM on behalf of the CAS, CADWorks and Analysis Solutions division. And today my co-presenters, in fact the main presenters today will be Chris Bradshaw, who's a business development specialist at Hexagon PPM. Chris has significant experience with the support and the training of CAESARII. And I'll be joined by Mark Groon, who is a senior engineer at our partners Dynaflow Research Group, who are the developers of the BOSfluids program. So I just want to say a little bit about the agenda. First of all, if any of you saw the webinar maybe 2 or 3 months ago now by Jim Wilcox of CodeCAD, this was an excellent webinar on the similar subject. It was on surge. It was very well attended, and there was a lot of interest after the webinar. So that's what made us decide to follow this up with a second webinar, but this time showing you how CAESARII works and integrates with the BOSfluids program. So what we'll cover is a summary of the surge events and a little bit of theory and why we need the software to avoid the consequences of various types of surge events. We'll then give a brief description of how BOSfluid itself works and how it can help. And that will be followed by a couple of slides which illustrate the workflow and how the two softwares integrate with respect to geometry and data, in addition to what kind of data needs to be added to the respective fluid and mechanical analysis programs. That will be an overview. Then we'll move on to a live presentation where we'll show you that workflow in practice on a real example. And I want to point out that during these stages, we will also be talking a little bit about what the new capabilities in BOSfluids version 5.4 offer to us. This was released just a few weeks ago, and it gives us some additional capabilities and productivity benefits. After the main live presentation, I will give a short summary on what we can expect by a new product that's about to be released in a few weeks' time. It's called BOS B31. So I'll give you a sneak preview of that before we close out and go on to the questions. So with that, Chris, I'll hand over to you to start the presentation.
Okay, thank you, Steve. So in this first part of the webinar, we will look at surge events in a piping system, looking at what they are and what can cause them and the effects of those surge events. And then, of course, we'll look at how we can evaluate the effects easily using CAESARII and BOSfluids together to avoid failures. So what are surges? Well, simply, surge events are variations in pressure that are generated by a change in the operational status of our piping system. And there are several changes that can lead to surges in a piping system. These may be foreseen operational changes, such as our pump startup event, or they could also be unforeseen operational changes. This could be something like the rapid closure of a valve, or perhaps a pump trip event. Or additionally, changes to the layout of the piping system could also cause a surge event. But whatever it is that causes a surge event, these events can lead to unanticipated effects, such as extremely high or extremely low pressures in our piping system, or unbalanced forces, which can lead to pipe movement. So what are the consequences of these types of surge events? Well, changes in pressure can lead to pressure differentials, but in particular on long straight runs, which can cause large unbalanced loads leading to pipe movement. In the image which we see here in the top left, the pipe highlighted in red is supposed to be sat on the pipe rack along with the rest of the pipes, but the movement of the pipe has caused it to move significantly, and it's now sat resting on the other pipes where it should be sat on the pipe rack next to. Pipe movement can also lead to overstressing and failure of supports, which can lead to failure of the pipe as well. Here in the image we can see that there has been some significant axial movement, which has caused failure of the pipe shoe, and also the I-beam supporting the pipe shoe has also been bent, quite a large force there. In addition to the pipe movement, we can also have very low pressures. These could cause collapse of the pipeline, which is highlighted in the clouded area here, or the opposite of that, conversely, we could see very high pressures in the pipeline, which can lead to pipeline rupture. Now, of course, it's always better to prevent these situations. We want to avoid them. So if we prevent these situations through analysis, rather than rectifying after the event, that's of course much more preferable. And CAESAR-2, as we know, can be used to evaluate the effects of these unbalanced forces acting on the piping system. But in order to do that, we need to know what those forces are, and calculating these forces can be quite complex. As an example, if we look at the rapid closure of a valve. Now, when we close the valve, then the approaching fluid column will stop. And what that does, that causes a pressure wave to be generated. And the maximum amplitude of that pressure wave is the Yukovsky peak. And that is calculated by the fluid density multiplied by the change in velocity multiplied by the speed of sound. And then that pressure wave will flow back through the piping system against the direction of flow. And it will be something along the lines of like so. Now, if we were to freeze the piping system at a point in time, then you can see here we have a pressure differential. We have the low pressure on the left-hand side, which is indicated by the lighter color, and the high pressure on the right-hand side, indicated by the darker color. So you can see we have different differential pressures along this straight leg. We have a low pressure and a high pressure. And those pressures will lead to a force. The force, of course, being pressure multiplied by the area. And on the left, we have a smaller pressure, so smaller force compared to the higher pressure, therefore higher force on the right-hand side. This ultimately ends up with giving us a resultant force acting on our pipeline, which leads to movement of the pipeline, something like shown here in the dotted line. In addition to that, once the pressure wave flows back through the system and reaches the end or a stop point, then it will reflect back and go back through the piping system. And these reflections give a passing frequency on the surge event. And that passing frequency depends on the geometry of the system and also the speed of sound in the fluid. And if the passing frequency couples with the mechanical modes of our piping system, then that's where the severity of the surge event is greatly increased. And we can end up with resonance if the two frequencies are close to each other. So these manual calculations, the Yukovsky simplification, let's see why is this insufficient and what is the benefit to a user, someone using BOSfluids. So if we take a look at with a very simple piping system here, this one is 16-inch nominal size, 8 bars of pressure, and a 2.35 meters per second fluid velocity. And if we look at the Yukovsky simplification, we can obtain a change in pressure, which is, as we said earlier, the speed of sound of the fluid multiplied by the density multiplied by the change in velocity. And that will give us one value for a change in pressure, and that will be the maximum amplitude of the pressure wave. Now, if we compare that to the BOSfluid results, we get, as well as this a peak value for the pressure, we also take into account, BOSfluids can take into account the reflections of the pressure wave and the passing frequencies. Now, on this particular system, the force computed using the Yukovsky simplification comes out at 417 kilonewtons. That's quite a high force. It's rather significant. If we compare that to the BOSfluids results, the peak force that we get, the highest force, maximum force anywhere in the system from BOSfluids, comes out at 41 kilonewtons. And you can see straight away, this is pretty clear. That's a factor of around 10. It's actually 10.16 in terms of the difference. Now, if we were to carry on with the Yukovsky simplification and not use BOSfluids, then we would be trying to resolve this piping system to deal with a 417 kilonewton force. And of course, that would need some significant modifications to the piping system. we'd need a considerable amount of more steel, perhaps more piping, more concrete to support the steel. Whatever the resolution was, though, we would most likely need a fair amount more time and space, and ultimately that would lead to more delays, and it would be a much more expensive piping system compared to if we would use the BOSfluid results and handle a force which is a tenth of the Yukovsky simplification method. However, that's not the whole story, because we don't really know if we are conservative or not using the Yukovsky simplification. And whilst that simplification can greatly overestimate the effects, with the force being 10 times it was in our little example, what this doesn't take into account, because it only gives us one value, is it doesn't take into account the reflections. So the converse of that, we don't know if the frequency of the surge event due to those reflections matches up with a mechanical natural frequency of the piping system, and we don't know if we have resonance. And all of this, coupled with the complexity of a real-world piping system, means that the only way really to be sure is to use some software, such as BOSfluids, to evaluate the surge event. And that brings me on to the first poll question of today's webinar. So, Carol, could you please ask the first poll question?
Certainly, Chris. Thank you. We're going to move on now to the first poll question. So, how often do you perform flow surge analysis? Never, occasionally, when there is a specific issue, or frequently? We will now wait a short moment to give everyone the chance to answer their question. Well, we got 23% that said never, 66% occasionally when there is a specific issue, and 11% of the people answer frequently to how often do you perform flow surge analysis. Chris, we're back with you.
Okay, thank you, Carol. So those results were interesting, and I think that's what we expected, with only 11% of people frequently evaluating surge events. And I say it's expected because the surge events are traditionally seen as quite complex. So let's now carry on with the next part of the webinar to see how CAESARII and BOSfluids can simplify and streamline that process. And for those of you that only do it when there's a specific problem, perhaps see how you can use these tools as a preventative tool rather than a forensic tool. So, as we've seen, surge analysis of transient events can be performed in software such as BOSfluids to predict the forces throughout the piping system, and we can then take those forces and use them in a mechanical pipe stress analysis program such as CAESARII. The key thing here is that CAESARII and BOSfluids work together to make this process much, much easier. So how does this process work? Well, the basic workflow is you build your model in CAESARII and run the static analysis just like you do today. And then once your static analysis is complete, your pipe system, everything is satisfactory, you can then convert your CAESARII input to a CAESARII neutral file. And that CAESARII neutral file can be read directly into BOSfluids. Here we see a screenshot from BOSfluids, and you can see the file type is a CAESARII neutral file. We can read that directly into BOSfluids and create a BOSfluids model, which is now available and ready for steady state and transient event analysis in just a couple of seconds. Also, BOSfluids version 5.4, the newest version, also supports PCF files. So depending on what information and what files you have available, you can also use PCF files in your workflow. So we can generate a BOSfluids file quickly and easily directly from CAESARII simply using the neutral file. And then once we have that file model available in BOSfluids, we can then define the boundary conditions for the steady state analysis to set up the flow analysis. So these are things like fixed pressure or fixed flow rates at the boundary of the model, at the ends of the model. Then if we do have a transient event, in this case a sudden valve closure, but this could be something like a pump trip or a pump startups, anything like that, you can then define those parameters. So here for the sudden valve closure, we define the valve. You can define how the valve closes. You can define the valve CD curve, and then also define the closure in terms of timing as well. And then run the transient analysis in BOSfluids, and we get some results. So the results for this example, here we can see in the top left corner a short animation showing the pressure wave reverberating through the system. And this 3D output, which is a byproduct of having a 3D model available in BOSfluids, this can show various parameters for the duration of the transient analysis. So you can choose how long to run the transient analysis for, and you can view the results at any time slice during that transient analysis. You can also play it back as an animation. And you can view things such as in the top left corner, we're viewing the pressure, but we can also view the force, the fluid velocity, the flow rate, and the fluid, and so on. You can also create different scenarios in a model, so you can try various parameters without having to create a new model. And in the latest version, BOSfluids 5.4, during the analysis, the scenarios are run in parallel on different processor cores, which really decreases the analysis time. And for the results, as soon as the first scenario has completed, you can access the results for that scenario, and then other scenarios become available as and when those analyses complete on those processor cores. In addition to the 3D output, you can also produce 2D charts, 2D output, to plot the required results at any location in the system. And you can plot multiple charts on the same graph. So here we see a force time profile for a particular node in the piping system. You can also view the same results as we saw in the 3D model, so the flow rate, the pressure, the velocity throughout the system, and for any scenario. And as you can plot multiple charts on the same graph, you can plot multiple scenarios or multiple parameters on the same graph. As well as being able to view the results in the time domain, you can also have the option to view in the frequency domain as well. So you can get a quick check to see if your frequencies of the surge event are close to the mechanical natural frequencies of the piping system. And there's also the option in BOSfluids to quickly and easily view the maximum value at any point in time throughout the transient event to make a quick check to see if this event may cause an issue. So here we can see that the fluid hammer event has caused forces up to around 90 kilonewtons, and these high loads may be a concern. We can find out if they are a concern because we can take them to CAESARII 2. So once the analysis is complete, if you are concerned, if you do have high loads and you want to take them to CAESARII 2, this is a simple matter of choosing to export those forces. And BOSfluids can export the forces into a file format which CAESARII 2 can read and is familiar with. It's just a matter of selecting which force pairs to export. And the force pairs are, which legs we want to export from the piping system. And in BOSfluids 5.4, these force pairs are automatically generated, so each leg has a force pair generated for it automatically. And these are presented and ordered by the highest forces first, and then it's a simple matter of ticking the tick box to choose which forces you wish to export for taking into CAESARII 2. Typically, you wouldn't export every single leg. It's the longest legs which would be generally the most or greatest concern, because that's where the pressure wave is at its highest for the longest, so it's where we get the highest forces in a system. But once you've chosen which forces to export, then you can take those into CAESARII 2's dynamic analysis processor and read them in to the dynamic module, simply clicking the read from file button, which you may be familiar with if you use CAESARII 2's dynamics, to import the force time profile, which then you can perform a time history analysis of the transient event. After reading in the force time profiles, complete the setup of the dynamic analysis to apply the force time profiles in CAESARII 2 at the correct node numbers, and then run the CAESAR2 dynamic analysis. So let's see how that works with a live example. So I have CAESAR2 running on my machine, and I'm going to start off. I've got a file already open, the hammer event. It's the same one as we saw in the PowerPoint presentation. So I'm just going into the piping input, and the model's already been built, so there's not a lot for me to do at this point, but I just want to quickly take a look at the model. So you can see here we have a valve down at node 20 to 30. This piping system is 60 degrees and it's 17 bars pressure. Here you can see the node numbering system and various restraints throughout the system. So this is already being set up, and there's anchors at either end. So all I'm going to do, I've already built the model and set up the temperatures and pressures and so on. So all I'm going to do is run the error checker. There are no errors and no warnings. So I'm just going to run the static analysis using the recommended static load cases. Here in the load case editor, I'm happy with these load cases, so I'm just going to click run the analysis. And here we see the static result. Now, for the purposes of this presentation, I'm not going to spend any time reviewing the static analysis results, but suffice to say we have no load cases shown in red, so in terms of a stress standpoint, this system is perfectly fine. So I'm going to now finish with the CAESAR2 static analysis, and I'm going to assume that I'm happy that everything is okay here, and I'm going to now go to interfaces, and in preparation for doing the flow analysis in BOSfluids, I can generate a CAESAR2 neutral file. So I'm just going to convert the CAESAR2 input file to a neutral file, browse to the CAESAR2 input file, which is this one called hammer, the A file, which is the input file, and convert that to the .cii CAESAR2 neutral file. The conversion takes, if you've not done this before, it takes a split second, as you can see. And no, I don't want to perform another file conversion. What I want to do now is hand over to Mark for the BOSfluids portion of this presentation.
Hi, Mark, is with you.
All right. Well, thank you, Chris, for the first part of the demonstration. So, in this second part of the demonstration, I'll go to BOSfluids, and I'll show you how to perform the flow analysis in BOSfluids. So, right. First of all, when we start up a new file in BOSfluids, we'll just give it a name, water hammer. And in BOSfluids, at the right-hand side of the left part of the screen, you will have the piping model. And and at the left part of the screen, also the input fields. The input fields will show you the basic workflow through the model. So in the first tab, you will start by creating a piping model. In the second tab, you'll input all the parameters. A third tab, you'll run the actual flow simulation. And in the fourth one, will have to you can review the results. So building a piping model in BOSfluids is quite intuitive if you are used to CAESAR. So you start with building the elements between nodes. So you give it dimensions. BOSfluids has all kinds of various element types available. So next to the standard pipe, you can also define valves, pumps, or even search vessels, etc. So a new feature in BOSfluids 5.4 is that you can also use the nominal pipe sizes. So if you just specify an 8-inch pipe and a standard schedule, this will bring up immediately the correct diameter and wall thickness for that. So for the today's presentation, we'll going to run through the water hammer example. So we can just go to import model and just browse for the hammer CAESAR neutral file we just was just created by Chris, and we'll click on import. This will brings up some of the import options. You might want to merge some of the elements to optimize it for the flow simulation, and you might want to keep the rigids which are specified in CAESAR. All right, so importing the model is done like that. So this brings up the same model as we just saw in CAESAR. The node numbering and the coordinates of all the nodes are equal to that in CAESAR. So with that, we actually can skip this first tab where we are going to build the model, and immediately go to the second tab where we will see what to you will use for the input parameters. So in this first one, we can BOSfluids lets you quickly identify the rigid elements which were specified in CAESAR because they are probably some special elements. So for instance, this rigid element over here, which was defined, which has to be defined as a valve. So we can click that valve and we'll configure the valve. We can select a typical valve curve you might want to use. So we can specify which kind of valve we're going to use, a ball valve, a globe valve. All right. And furthermore, we can specify some valve actions for this valve. So what I would typically like is for the first time just to keep it in a steady state. So we'll keep the valve opened for the first second, and after 1 second we'll start a transient event, which will be we're closing the valve in 1.4 seconds to be completely closed. All right. So with that, we can confirm this, and we have specified the valve. All right. In the second step, we can specify the boundary conditions for this model. BOSfluids, when importing from CAESAR, also lets you quickly identify which nodes are at the boundaries, because those are the points where you might want to specify a boundary condition. So at this first node, we'll specify it to have a fixed pressure of 17.2 of 16 bar, right? And at the second node on the other side of the model, we'll also specify to have a fixed pressure at 17.2 bar. All right, this will complete this part of the model, and we'll can define an analysis type. So BOSfluids has a couple of analysis types, steady state, but for this one we'll use a transient analysis. BOSfluids also gives you the option to include a cavitation model while performing the flow analysis. But for this demonstration, we'll just use the regular transient analysis type. And this will gives you all kinds of additional options. We might want to specify or leave at default. For this analysis, I would like to override the automatic simulation time with a specified time. So we're going to run the simulation for 10 seconds. And as Chris already explained in the slides, previous versions of BOSfluids would require you to specify force pairs. However, in this new version, this is no longer required, and when exporting the forces, it will automatically calculate all possible force pairs for you to export. Okay, so as we conclude I've concluded all the settings for this scenario. This second tab is actually called scenarios because in BOSfluids you can also specify additional scenarios which are a variation on this particular scenario. So I've already done this for this model, so let's quickly open that model. So this is the same model again, but now I have included two additional scenarios, one where the valve will close faster, so in 0.2 seconds, and one scenario where it will actually the valve will close more slow in just 1 second. All right, when all the scenarios are set up, we can go to the third tab where we actually perform the flow simulation. So as you can see, it already calculated all 3 of the scenarios right now. So that's rather fast because it's quite a small model for this demonstration. But it as in BOSfluids 5.4, it now runs on various processing cores. So when you have large models, you can actually perform your flow analysis much quicker. All right, so now we can go to the final tab where we can view the results of our flow simulation. And the results are presented in various ways. So there's a 3D model which will show you the data sets projected on the 3D model. We have various output reports where you can see them in text files, and we can generate 2D graphs for all the data sets. So for instance, if we start a graph where we'll show the complete pressure profile of the simulation, we'll get a graph like this. So, and we can use the slider to actually go through the simulation, and we'll see can quickly identify for this particular graph the maximum pressure and the minimum pressure and the current pressure at that time along the whole trajectory actually of the model. We can also go to a specific point in the model just by double-clicking that node, and it will generate a 2D graph of the actual pressure at that point. So what we'll see here is that after 1 second, when the valve closes, we'll get an initial high peak pressure, and after that initial peak, we'll see a bunch of reflections going back and forth through the system, where actually the pressure waves bounces off the boundary condition at the other side of the other end of the model. We can also use these graphs to show the differences between our scenarios. So for this 3 scenarios we just created, we can analyze these ones. So compared with the main scenario, the scenario where the valve closes faster, we have a higher initial peak and higher reflections. While when we close the valve very gradually, we actually see very low pressure peak and then very shallow reflections, almost none. What is of particular interest in a dynamic simulation is also what is the acoustic frequency. We can just on the bottom left change to the frequency domain and take a look at that, and we see that the main frequency of this, the acoustic frequency of this simulation is actually at 4.2 Hertz. So you might want to take that into account and compare that with the mechanical modes of the model, and see if none of the mechanical modes can cause a resonance with this 4.2 Hertz of the acoustic frequency. So what we're actually going to do is we're going to export the forces to CAESARII. So we can identify them in the 3D output, and we can take a look at the maximum values, the maximum forces. So as Chris explained, the highest forces will be at the longest stretches of pipe. So at these stretches between this node 100 and 160, and these nodes 190 and 230. All right, so with that we can use our tools and export these forces. The forces can be exported to also to text files or simple Excel files, but for now we'll use a format that CAESARII will easily recognize. And as Chris showed, the data files we're going to export for this demonstration will just be the forces on the two longest stretches, which are these first two, and we'll just hit the export button, and this will create actually the force files which with the complete time history of the forces, which can be read in by CAESARII. So with that we can go back to Chris and let Chris show you how to perform the dynamic analysis in CAESARII using these time history files.
Okay, thank you, Mark. So as we've seen, we can do the flow analysis in BOSfluids very, very quickly, because the majority of the time spent generating the model is now done automatically by importing the CAESAR2 neutral file. So Mark has generated the force time profiles. I can now take those and in the CAESAR2 dynamic analysis module perform a time history analysis. So first thing I need to do is choose to do a time history analysis. And what I'm also going to do is I don't need any of the standard default spectra, so I'm going to delete those rows and add in 2 rows for my spectra. So I'll just give these names, and I'll just give them a simple name. We'll see, I've got one from force set between node 100 and 160. These, of course, will be time versus force, and I will choose linear interpolation between the points that I specify. And I'll do the same for the second force set, which is along the leg between 190 to 230 as the node numbers. Again, time versus force and linear interpolation. So now I've defined the time history definitions. I actually need to put in the data. So if I can click on the define spectrum icon and just define the 2 spectra. So for the first one, 100 to 160, I'll just double click. And all I need to do here is click on the read from file button and locate the files generated by BOSfluids. These are these two .dat files. So this first one, 100 to 160. I'll choose to open that file. It reads in the data. Now with CAESAR2, we don't see the chart plotted until we close and reopen. But here we can see the data for 100 to 160. There we see the initial pressure and then the reflections, just like we saw in BOSfluids. And I'll do the same for the second force from 190 to 230. Again, if I just close and reopen, so we can see the plot, and also notice that the force magnitude is defined in the force time profile as well, which means now that I've completed that, on the next page of the dynamic input, the force sets, I define my force set simply by specifying the force magnitude of 1 here, and then specifying the direction. Now these directions, these forces, these legs are both in the X direction. And node numbers, these are, I'll apply these at, for the purposes of this demonstration, I'm just going to apply the full force at the elbows. Perhaps, maybe you'd want to do this a little more, perhaps accurately, by applying half the force at this first elbow, half the force at the end elbow, depending on how you want to apply the forces. But for the purposes of this, I'm just going to apply the full force in the X direction at the elbow at 160 and 230. And I'll call these force sets number 1 and 2. The next stage is to set up the time history load case, which is simply combining the time history profiles with the appropriate force set. So it's applied at the correct node number. So 100 to 160 profile, apply it with a factor of 1 again in the X direction, and combine that with force set number 1, and then 190 to 230, also in the X direction, combined with force set number 2. And then if we're interested in looking at stresses, we need to create the static dynamic combination load case. So I'm going to add a new load case. I'm only going to create 1 here. And as is typical, I will combine the sustained load case from the static analysis with my single dynamic analysis load case, as is typically done for the occasional load cases, keeping all the primary loadings together. And in this model, I don't have any lumped masses and I don't have any snubbers, so I can go straight to the control parameters tab and set up the time history analysis parameters. So first of all, the static load case, the nonlinear restraints, I'll choose the operating load case. And I don't have any friction in this model, keeping it simple for the presentation. So I don't need to worry about the friction. And the 33 Hertz cutoff should be fine. The surge frequency, if you remember, was about 4.2 Hertz, so 33 is fine. And then for the time history time steps, I'm going to do a 5 millisecond time step. And I'm going to run the analysis for 10 seconds, which was the same as the surge analysis was run for in BOSfluids. And I will say, okay, I want 10 time history load cases. 3% critical damping is fine, and I will choose the consistent mass model. Shouldn't take too long to run. And that's all I need to do. I don't need to touch the advanced parameters, so I can go straight and run the dynamic analysis, the time history analysis. So first of all, we extract the natural frequencies of the system, and if we see anything around 4.2 Hertz, then we might have an issue. But fortunately there wasn't. We got 3.8 and then 5.4, so I don't think we should see resonance in this situation. So the natural frequencies are being extracted, and now we do the time history analysis. It takes a few seconds because I had 5 milliseconds for 10 seconds. And here we have the analysis results. So it really was very, very simple, bringing the data from BOSfluids straight into CAESAR2 just by reading from the file. And then it's a simple matter of setting up the time history load cases. So in terms of the results, I'm not going to spend too long looking at the results here, but if I just go straight to the occasional combination case and just look at the maximum response and maybe look at stresses. Well, the stress levels are the kind of high 86, 87% of the allowable, but they are within the code allowables, so we're not exceeding. We don't see any red text, at least in CAESAR 2's terminology, so we're okay there in terms of stress. It's a little high, but not over the limits. Perhaps we take a look at restraint loads to see what's the maximum restraint loads and when they occur. At node 10, there's nothing enormous, so maybe 5 kilonewtons Y force. And if I scroll down, then what I do see, however, is some high loads at the opposite end, anchor at node 240. There is a pretty high bending moment here, 41,000 Newton meters bending moment at the opposite end. So maybe we need to take a look at resolving this. But for the purposes of the presentation, that's the end of this part of the presentation in terms of the live demonstration. So I'm now going to go back to the PowerPoint presentation, and in fact that brings us on to the next poll question. So Carol, could you please ask the second poll question? Thank you.
Thank you, Chris. Yes, our second poll question is, have you experienced issues with flow-induced vibrations? Yes or no? Please answer. So we got 70% of registrants who replied yes, while 30% replied no, to have you experienced issues with flow-induced vibration. Chris, this is back with you.
Okay, thank you, Carol. So 70% of people say yes, they have experienced issues with flow-induced vibration. Well, that's interesting, and it's interesting to us, and hopefully I'm about to hand over to Steve, but what Steve is about to show is, I think, likely to be interesting to particularly those people who have experienced issues with flow-induced vibration. But I think most people in our industry, to avoid effects of vibration on pipes. So, Steve, if I now hand over to you.
Yeah, thanks very much, Chris. Yeah, I'm pleased the poll result was as it was, because I certainly experience when I speak to EPCs, large engineering companies, they talk about vibration a lot. So I think it's something that's out there and causes problems in many cases. So I'm going to give you a brief overview in the next 5 minutes or so, and then we'll wind up with questions of the new BOS B31 utility that's going to be made available in the next couple of weeks. It's really to address well, it's not only to address this, but one of the references is the B31.3 paragraph 301.5, which I'll come to in a moment, which talks about hydraulic force estimates and particularly vibration. So this BOS B31 utility you will see appear in the version 3.1. You see at the top of the banner here, version 3.1 of FEA tools, and I'll say why FEA tools in a moment. But 3.1 of FEA tools is going to be released in the next few weeks. It's to coincide with the version 10 of CAESAR 2, which is due out, I think, in August. So those two programs kind of go hand in hand. If you're not familiar with FEA tools, then you see the menu on screen now. I'm just going to blank out a couple of those utilities because they are not included in the FEA tools module. But very briefly, FEA tools is there in order to enable you to create more accurate models, piping system models, particularly in respect of bends and tees, in giving more accurate SIFs and K values. Now, the translator, you see the translator module top left there. That's the module that's used mostly in conjunction with CAESAR 2. What it enables you to do is bring in the newly released B31J SIFs and K values that are now available to everyone. The conservative values that have been used for many, many years have now been replaced by these values in B31J. So the translator allows you to do that, but it also allows you to bring in much more detailed data and additional data that's calculated by finite element analysis. So not only can you calculate very accurate sifts and flexibilities for T's and bends, but there are additional utilities such as vessel exchanger nozzles, flexibilities of those nozzles, also bends and trunnions when you've got trunnions on bends. API 661 header boxes are also addressed, in addition to allowable loads on nozzles and also on supports. So there are many things within version 3.1, but the BOS 3.1 utility, I'll just go back to the reason for the BOS 3.1 utility, and it's this. It's the para 301.5 in B31.3. And as you can see there, I've highlighted vibration because it seems to be a significant issue in many piping systems. So let me tell you a bit about how it works. In BOS B31, there are predetermined load magnitudes developed on an elbow or elbow T or a TT basis for each of a number of loads. And this is based upon momentum and the pressure in the flow. So examples of the types of predetermined loads may well be when you have a line that is downstream of either a reciprocating pump or compressor, an orifice, a flow control valve. If you think slugging is possible, you could have relief valves installed in the line. There are many occurrences that could potentially cause vibration in a line. And the idea is that when the user has a system, when there is a significant tendency to shake, given these load types, and I think there are maybe 12 or so load types available, then it indicates that a more detailed analysis should be undertaken in BOSfluids transient, which you've just seen. And both Chris and Mark have mentioned a couple of times the coincidence of the acoustic frequencies with mechanical frequencies. This is a very simple tool that allows you to assess whether there is likely to be a problem or not. So again, this is the menu that you see. And once you click on the BOS B31 utility, what you will see is that, first of all, just like you've seen in Chris and Mark's presentation, that there's a very close alignment with CAESARII 2. And it's a very simple 5-stage input. And this involves the computation of the mechanical and acoustic natural frequencies and the mode shapes. And this determines the tendency to vibrate and excite as a function of frequency. So when the user picks a loading mechanism, one of the examples I gave you previously, then we know in general how the momentum of the fluid will be altered, and as a result, the magnitude of the pressure wave that results. And from this, we can make some conservative assumptions that the waves act at every elbow pair through the frequency range, and the maximum displacements and the restraint loads are calculated using an SRSS, square root sum of squares approach. So that's basically how the program works. It's a very simple 5-stage process, which I'm not going to take you through now because of time limitations. But what I will do, I'll show you how the output looks. So again, there's the menu. BOS B31 is the utility, and it will address the likelihood of the everyday problem. I've called it an everyday problem because that's the message I'm getting from our customers of flow-induced vibration. So vibration induced by various flow types. So to repeat again, the acoustic frequencies are calculated due to the fluid flow. So as a result of disturbances around bends, T's, fittings, resulting from one of those load types that I mentioned. The mechanical frequencies, of course, can be calculated quite easily using CAESARII 2, as you've already seen. And then what we want to see is the results or the effects on the piping system. And as Mark mentioned just 5 minutes ago, if the acoustic frequency tends to coincide with the mechanical frequency, then you will have a tendency for resonance or vibration. So the end product of this utility within FEA tools is not only tabular information, but graphical information as well. So you have a plot, you'll see a plot of the acoustic and mechanical natural frequencies. So, of course, what we don't want to see is that the acoustic and mechanical natural frequencies coincide. And in this case, you can see there is potentially an acoustic natural frequency here at around 50 Hertz, with a mechanical frequency of around about 40 Hertz. Now, they're not laid on top of each other, so maybe there is no vibration likelihood in this particular case. But one of the reasons that we see this utility in FEA tools is because we know that the mechanical frequencies and the accuracy of those will affect the results. So it's really important that the mechanical frequency is calculated accurately. Now, for many systems, running this through FEA tools probably would not be required, but for many other systems that are essentially appearing to be rigid, then it is required, because if you run FEA tools to obtain a model with the accurate bend, vessel and nozzle flexibilities, such as systems, maybe high D over T systems, where ordinarily you would assume that nozzle connections and T's with a high D over T have a kind of an infinite stiffness because K equals 1 in the codes. In practice, we know that's not true. So if you ran that through FEA tools first, you get a different natural frequency, which could result in it coinciding with the acoustic frequency that you've calculated from your loading type. And then if they coincide, you know you have a real potential for vibration and the possibility of running a more accurate analysis using a transient model in BOSfluids. So that's just a brief overview. That's coming to us in a couple of weeks' time with the release of FEA Tools version 3.1. It's called BOS B31. I'd encourage you to take a look at it if you do have any problems at all with vibration, because this utility could help you prevent that. It causes a lot of issues. Okay, that's all I want to say on BOS B31. So with that, I think, Caroline, we can go over to the Q&A session.
Thank you, Steve. We're going to proceed now then to the Q&A session. Just as a reminder, please make sure to use the question box on the right-hand side of your screen to type your questions. And we're going to start with the first one. What about gases? Can BOSfluids deal with fast closing valves in steam systems?
So I think I'll answer that question, Mark here. All right. Well, BOSfluids can handle gases as well. The demonstration we just gave was with the fluid type water, but BOSfluids will also allow you to specify a user-defined fluid, which can be a liquid or a gas, and ask the user for inputting all kinds of parameters specifying the gas. And a gas will actually behave quite similarly when having a valve closure and or a steam hammer effect. So yes, that's possible.
Thank you, Mark. Second question: is there an invitation on BOSfluids regarding system complexity, numbers of branches, boundary, etc.?
All right, I'll answer that question as well. So, of course, there are limitations, but they are set very high, so users will probably never encounter them. There are simulations performed with BOSfluids using thousands of elements, which will actually take quite some time to run in terms of flow simulation. So the limitation of the number of elements will not be a problem.
Thank you. We're moving to our third question. Why the difference of force between manual and BOSfluid?
You want me to take that, Mark?
Yeah, sure, Chief.
Okay. I think this is a pretty simple one, and it's something I was involved in many years ago. It's really the difference between an assumption of instantaneous closure and what we see in the real world. And Chris's example there, where he had a factor of 10 between the Joukowsky head force and the BOSfluids force, was simply due to that. The Joukowsky head equation assumes the delta V part of that you put in the velocity of the fluid, and the velocity of the fluid, let's say it's 8 meters per second. If you put the delta V in as 8, then it's assuming that the event happens instantaneously, which of course never happens. Even in steam systems where I used to be involved, the valves closed quickly, but not that quickly. They weren't instantaneous. And in most water hammer situations, then the valves are closing in, I don't know, at best half a second, maybe longer, 3/4 of a second, just over 1 second. So in reality, the closure is not instantaneous, so that delta V is not equal to the velocity of the fluid, it's something less. And that's what BOSfluids calculates accurately, I believe, using the method of characteristics, Mark. Is that right?
Yes, that's correct. Yeah.
Okay.
Thank you, Steve. Thanks, Mark. We're going now to answer the last question of today's session. Please note that we have several questions that have not been answered yet, but the time slot for this webinar is coming to an end. We will provide you with answers by email afterwards. Do you apply the same force on elbow spare or force based on pressures at each elbow?
So let me answer that one. So if I understand correctly, it was about performing the dynamic analysis in CAESARII, where you had one force. So actually the force that's being calculated applies on the complete pipe section of that between those two nodes. So you only have to apply that force on one of the nodes, or if you will be a bit more accurate, you can apply half of the force on both elbows. So the force that comes out of BOSfluids actually represents the force which applies on the complete pipe section. So, but due to the input in CAESARII, you have to apply it on a node. So that's why it was done as shown by Chris during the demonstration.
Thank you, Mark. For those attending, in case of more questions, make sure to contact us after the webinar per email. This webinar has come to an end, and therefore I would like to thank our presenters, Steve, Chris, and Mark, as well as our participants from all over the world for being part of this webinar. I wish you all a great day ahead, and goodbye for now. This webinar is now concluded.